Okay, let's get started.
We're going to talk about derivatives. Yay! What a good day. Aren't you guys glad you're here on Friday? No. Oh, you better learn it. Trust me, you want to learn this stuff. Trig functions, they're going to come back at you again and again and again and again and again and again. Math 4B, oh yeah, that you spend most of your time doing trig. Even if you're not doing trig, you're doing trig. Trig substitutions, all sorts of stuff in 4B. Here we just get kind of basics, so you're lucky. You're lucky, but you really need to handle this stuff so that you next class, oh, you look so depressed. So that next class you get it. You ready? I'm going to prove it to you at least so you know where it's coming from. Would you like to see that?
Yes.
Okay. There's two things we need to understand, and they all start from here. Please tell me you know those. Do you know those? Please. What's this one? One. Very good. What's this one? Good. If you know those ones, I'll prove to you that we can find the derivative of sine, cosine, tangent, secant, cosecant, cotangent. Those are our six that we're going to be working with a lot in this class. Okay. You got to memorize those derivatives. I'm not going to show you all of them. I'll show you one of them. The other, I'll show you sine right now. The one for cosine is very similar. The one for tangent, cosecant, secant, cotangent can be done with the quotient rule. Because once you have sine, you have a lot of it pretty much done. You ready for it?
What we're going to do in this video is prove that the limit as theta approaches 0 of sine of theta over theta is equal to 1. So let's start with a little bit of a geometric or trigonometric construction that I have here. So this white circle, this is a unit circle. Let me label it as such. So it has radius 1, unit circle. So what does the length of this salmon colored line represent? Well, the height of this line would be the y-coordinate of where this radius intersects the unit circle. And so by definition, by the unit circle definition of trig functions, the length of this line is going to be sine of theta. If we wanted to make sure that it also worked for thetas that end up in the fourth quadrant, which will be useful, we can just ensure that it's the absolute value of the sine of theta. Now what about this blue line over here? Can I express that in terms of a trigonometric function?
Wait, why is that again? Man, my brain is so fried. I don't... Like... I haven't done trig in so long. Shall I look up a proof of the unit circle again?
Let's just think back to where we began, right? We said this topic is called trigonometry, right? Which is just about measuring triangles. That's what the name means, okay? But very, very quickly, we moved from trigonometry to a very specific part of trigonometry, namely all this sine, cos, tan business, right? Now, these are not trigonometry, they're just one part of it. They are the trigonometric ratios. And we went over this in our first trig lesson. We said SOHCAHTOA, opposite, hypotenuse, adjacent, all the different combinations of those give you ratios, and we give them names, and that's where we started, okay? But you quickly realize that this is a very limited way to define these things, and therefore this, right? Because have a look. Here's a typical right-angled triangle, right? And if you wanted to work out what sine of theta or cos of theta or tan of theta and all of the reciprocals are, you're kind of limited, right? So you've got your opposite, your hypotenuse, and your adjacent here, right? So you can get different ratios, but theta, and we noticed this in our proof by contradiction about the tangent being perpendicular to the radius, we notice that theta automatically is locked into a certain domain. There are restrictions on theta. What are the restrictions?
That's 0 and it's in between 0 and 9.
Good. So yeah, theta's acute, basically, right? This is a problem because if we want to understand angles, right, you don't even have to leave triangles. If I just push this triangle over to the side, right, like so, okay, like there's an angle over here. Let's call that alpha. Can I do trig with that angle?
Yeah.
Like, if I look at this, I can't because it's not acute anymore, right? So here, my definitions, my very, very narrow definitions of the trig ratios, they immediately break down, right? And then what about trig when the angle's not in a triangle, right? Where's the opposite and the there's no hypotenuse. What do I even do, okay? So this is a nice way to start. Right-angled triangles are a good beginning, right? Because they're understandable, but they're no good, right? When you think about obtuse angles, or reflex angles, or bigger angles, or what about just boundary angles? What about 90? Oops, right, I have a 90 degree there. What's sine or cos of tan of 90? How do I work out what these are? This definition isn't going to fly, okay? And that's why what we're going to do is we're going to take this definition and we want to understand not just ratios, we want to move toward trigonometric functions. I want you to think back to the first time you heard the word function, right? What is a function? What's a function?
F of x.
We tend to write it with the abbreviation f of x, right? A function is just something you can stick a number in and get a number out. Excuse me. Thank you. Okay. Simple concept. Stick a number in, we call it x. And out will come another number, and we call that f of x, right? And we know all kinds of functions already. 2x, 3x minus 1, x squared, log of x, blah, 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 okay? So what we want is, can we define sine or cos and tan in a way such that I can put any x you like, right? Not just within this little spot, such that I can get a value out the other end. I want to generalize. I want to blow open my world and not be stuck in right-angled triangles anymore, okay? So the way we're going to do this is with a circle, not just any circle. This is the unit circle, okay? So it has a radius of 1, right? There's a radius of 1. Now, the unit circle is inextricably tied to the trig ratios and the trig functions. We shouldn't be that surprised because, as we were just explaining, you know, even one of the basic functions, namely tan, is named after a component of a circle, right? So we should expect that there's some kind of link here. In fact, in some of the older textbooks that you'll have a look at, when they're looking at trigonometric functions, the chapter isn't even called trigonometric functions. It's called circular functions. Sine, cos, tan. That's what they're called, right? So fundamental is the circle to understanding these, okay? So here's the way we're going to go through this. Here's your unit circle, and we're going to put one of these right-angled triangles in our circle, okay? So I'm going to put it right here in the same orientation as my, oh, that's not very well, that'll do, okay? As my triangle over here, okay? So, there we go. Now, I put it here, and so I'm going to put my theta in the same spot as well. So I actually have a full triangle here. Now, before I go any further, I want to immediately draw your attention to the fact that, why do I start here? I start here very on purpose, okay? And it seems a bit confusing because we have measured angles around a cross-looking thing before when we did bearings. Remember that? Okay, bearings, we've looked at this. But this is a bit weird. Let me show you. When we do bearings, we know how to do north, south, east, west, etc. Okay? But true bearings, which are measured all the way around, where do true bearings begin on a diagram? North, east, west. Where do they start? They start at north, right? True north, okay? And then we measure in which direction? We go clockwise, okay? Right? And this kind of makes sense, I suppose, for bearings, because north is a sensible place to begin, right? North, like your most important direction. And clockwise, well, it's clockwise because that's the way our clocks go, right? So why not measure that way? Okay, when we're in the unit circle and when we're in trigonometry, okay, things are completely different. So number one, north is not the starting point. Okay? Instead of north being the starting point, on here, it's east, it's the x-axis. That's our starting point, okay? Not only is that different, this is different too. We don't measure clockwise, we measure anti-clockwise.
Anti-clockwise.
Now, just
Australia?
before I give a bit of an explanation, I want you to have a think.
New Zealand?
Why do they do this, right? Why do they make them different? We're both trying to understand the same thing, angles, okay? Why on earth would they not only change the starting point, but the direction? As we go through this, I wonder if you will start to see why this absolutely makes sense in this context. In fact, if anything, the bearings are the ones which are a bit sort of arbitrary. Why start with north, okay? So that's an important note, and that's why I'm starting here on the x-axis, and my angle theta is measured anti-clockwise. You see that? So I'm going around the circle this way. Okay, now, what do I have a look at? Is this right angle triangle here? Okay, and just like in our very first question this morning, which is why I started with it, right? These sides here, I can phrase in terms of the trig ratios, okay? Now, if I say, okay, I've got a point up here on the circumference of the unit circle, okay? I want to know what its coordinates are. Well, its coordinates come from what's its x value, horizontal, and what's its y value, vertical, okay?
Okay, I remember why x is signed now. It's because the hypotenuse is 1 because the radius of the unit circle is 1. So you put opposite over hypotenuse, that's sine. Opposite would be okay, maybe I don't fully understand it, but it has something to do with the hypotenuse being 1, I know that. So you put opposite over hypotenuse, which is 1. I'll just keep watching.
Forget, it's the unit circle, so what's the hypotenuse equal to? 1. Okay, so down here, here's my x value. X equals, now what is x equal to, right? Well, I've got this side down here, and I know what the hypotenuse is. So being that this is theta, which trig ratio should I choose which will relate those two sides? It's cosine, isn't it? Because I've got adjacent, and I've got hypotenuse. In fact, you can just quickly mentally do it. Cos of theta will be adjacent on hypotenuse. X on 1, it's just x, right? So x is just cos of theta. That's what it's equal to, okay? In exactly the same way, when I look at y, I've got the opposite side this time. So sine of theta would be opposite on hypotenuse, it's just y. So y is equal to sine theta. So now I'm going to stop talking about x and y for a second, because I can relate those two sides. Well, I've got this side down here, and I know what the hypotenuse is. So being that this is theta, which trig ratio should I choose which will relate those two sides?
So is it just that they chose it because it's convenient?
It's cosine, isn't it? Because I've got adjacent and I've got hypotenuse. You can just quickly mentally do it. Cos of theta will be adjacent on hypotenuse.
That seems arbitrary though. This is x. This is 1. Adjacent hypotenuse x over 1. Oh, okay, no, okay, it makes a lot of sense because cosine equals adjacent over hypotenuse. Adjacent is x, hypotenuse is 1. X over 1 is x. X is cosine. Okay.
Hypotenuse. X on 1, it's just x, right? So x is just cos theta. That's what it's equal to, okay? In exactly the same way, when I look at y, I've got the opposite side this time. So sine of theta would be opposite on hypotenuse, it's just y. So y is equal to sine theta. So now I'm going to stop talking about x and y for a second because I can just talk in terms of theta, right? So when I name these coordinates up here, the coordinates of this spot are cos theta, sine theta, whatever
Right.
theta may be. Okay. So what have we done? We have taken this idea here about right angle triangles, right? And we've applied it to the circle, and then we've noted this interesting relationship that cos is the x coordinate of the point on the unit circle corresponding to this angle. Let me say that again. The cosine of theta is the x coordinate of the point on the unit circle that corresponds to that angle, right? And the sine of theta is the y value, right? So I'm now going to change gears. This is weird. I am just going to stop defining sine and cos in terms of this triangle. I'm now going to define sine and cos in terms of this circle, okay? Like in fact, I'll just go over here. If I drew a new unit circle, right, and I put like a dot over there, okay, I can define that point as cos theta, sine theta, no triangles involved, if measuring this angle around, that's theta. Do you see? This is a really big deal, right? Because, and this is why they're called circular functions, right? There are no triangles here. At least no triangles that I need to draw, right? Cos theta and sine theta simply come from where am I on the circumference according to what angle you've given me, okay? Does that make sense? Now, as you'll see in the next 5 minutes, this definition is so much better than our old definition. It's far more powerful, it's far broader, and it yields a lot of insights, okay? So, just before I leave this, okay, what's tan? What's tan?
Sine of cos.
It's just the ratio between the y and x coordinates, isn't it? Okay? So, all right, that's fine. Now, let's have a think about what this can yield for us. Okay? For example, let's come down to a point like here. Angle cos, right? One of
You
them.
can't make it root 3 over 2 either because it's greater than
Is here because the x-axis. Thank you. Is going right. What angle corresponds to this point? Coordinates of that point. That's going to be 1, 0. 1, 0, right? But we just defined those two numbers, 1 and 0, as the cosine and the sine of the angle related to this point, right? So 1 is the cos of an angle, and 0 is the sine of an angle, okay? So the question is, what angle corresponds to this point, right? And the answer is, the angle is 0 degrees, right? Because I'm measuring from the x-axis and I'm on the x-axis, right? I'm because it's this side, not this side. 360 is sine 30, which is a half.
it's a half more.
Okay. In fact, you can see I've drawn my triangle pretty well, right? Because look, it's about halfway. Because that's one over negative 1 over
You
there.
can't make it root 3 over 2 either because it's greater than 1.
Yeah, that's right. Okay, well, we'll get to that, okay? So I've got this side down here, because of 60. Now I'll work out this side. Well, it's the other. So now redefining cos is the x coordinate, right? So it's that far over, okay? So I can say this side here should be, well, cos of 60 will be this on 1, right? So cos of 60 is just that side. Cos of 60. Hold on, I know what cos of 60 is, don't I? It's cos of 60. Cos of 60 is sine 30, which is a half.
It's a half more.
Okay. In fact, you can see I've drawn my triangle pretty well, right? Because look, it's about halfway. Because that's one over, negative 1 over
You
there.
can't make it root 3 over 2 either because it's greater than 1.
Yeah, that's right. Okay, well, we'll get to that, okay? So I've got this side down here, cos of 60. Now I'll work out this side. Well, it's the other one, isn't it? So it's going to be sine 60,
Root 3
which is root 10. In each of these quadrants, sine, cos, and tan. Okay? Now remember, yeah, we'll get there.
That's why it's
Okay, so now I'll work that side, cos of 60. Let's do this one first. Okay. But cos of 120 and sine of 120 are equal to, and inside this triangle, I'm kind of stuffed, right? But on the unit circle, I can work this out. Here's how I'm going to do it. But on the
I'll
unit
watch some
circle,
videos for it.
so all right, that's fine. Now let's have a think about what this can yield for us. Okay. For example, let's come down to a point like here. Okay. Now I won't say anything yet about the angle. Tell me the coordinates of that point. That's going to be 1, 0. 1, 0. Right. But we just defined those two numbers, 1 and 0, as the cosine and the sine of the angle related to this point, right? So 1 is the cos of an angle, and 0 is the sine of an angle, okay? So the question is, what angle corresponds to this point, right? And the answer is, the angle is 0 degrees, right? Because I'm measuring from the x-axis and I'm on the x-axis, right? So that means that cos of 0 degrees is 1. And sine of 0 degrees is 0. Okay, I can keep going, right? You see, now I've got answers to these boundaries, right? Come up to the top. Come up to the top. What are the coordinates of this point? 0, 1. Right? Again, what's the angle that corresponds to that point on the circle? Answer, 90 degrees, right? So what this really tells you is that that's cos 90. Cos of 90 degrees is 0. And sine of 90 degrees is 1. Okay? Can you see what's happening here? We are breaking out of the triangle, right? I can now work with angles that are 0. You can't draw a triangle with 0 degrees in it. And I can do triangles which have, you know, only acute angles, but I can do 90 now, right? All right, excellent. Thank you. Okay, so I have some insights here, right? Let's keep going around and see what happens. I'm still up here, right? Let's draw an angle like, say, up here. Okay, now this time, right, because it's a point off in the middle of like wherever, okay, I don't know exactly what its values are equal to. So I'm going to go this time from the point of view of the angle. Okay, there you go. So remember the angle, this theta that we're talking about, starts from the positive x-axis. I have to say positive because it's this side, not this side. That's the negative x-axis. There's the positive side. And then I go anti-clockwise, right? So this angle, another color, is going to be a reflex angle. Okay? Is that so far? Oh yeah, sorry, I'm obtuse. Wrong quadrant. Okay. So what angle should I choose? For the sake of my illustration here, I'm going to make that 120 degrees. 120 degrees. Now, I want to know what cos of 120 and sine of 120 are equal to. And inside this triangle, I'm kind of stuffed, right? But on the unit circle, I can work this out, right? Here's how I'm going to do it. Okay, I'm going to pop down another vertical line there and make a triangle. Make a triangle on this side, okay? And the great thing about this is if I have 120 degrees here, because the x-axis is a straight line, right? I can know what this angle inside the triangle is, right? It's 60. Okay. Now, if I know that that's 60, I also know what the length of the hypotenuse is. It's 1. Okay. So now I can work out what this side is, which will give me the cosine, and what this side is, which will give me the sine. Right? So let's do this one first. Okay. What ratio do I choose? I choose cos. I choose it for two reasons. Number one, because it's adjacent on hypotenuse. But number two, because I'm now redefining cos is the x coordinate, right? So it's that far over, okay? So I can say this side here should be, well, cos of 60 will be this on 1, right? So cos of 60 is just that side, cos of 60. Hold on, I know what cos of 60 is, don't I? It's cos of 60. Cos of 60 is sine 30, which is a half.
It's a half more.
Okay. In fact, you can see I've drawn my triangle pretty well, right? Because look, it's about halfway. Because that's one over negative one over
You
there.
can't make it root 3 over 2 either because it's greater than 1.
Yeah, that's right. Okay, well, we'll get to that. Okay. So I've got this side down here, cos of 60. Now I'll work out this side. Well, it's the other one, isn't it? So it's going to be sine 60,
Root 3.
which is root 3 on 2. Okay, that's better. All right.
Do sine first.
So now what do I say? I want to know the coordinates of this thing. Okay. What's the x coordinate?
Minus half.
It's minus a half because I'm on the left-hand side of the Cartesian plane. Negative a half, right? And the y coordinate, well, it's above, so it's fine. That's root 3 on 2. Okay. So now, so this is brilliant, right? This is not a ratio. Minus a half. That doesn't make sense. Where in your triangle is your minus, right? And the answer is, well, 120. I'm outside that triangle now. Okay? But I have a meaning for it because the unit circle gives me a meaning. Let's quickly go down to here. Let's come down to here. Now, if I'm not going to draw a triangle because my diagram's getting pretty busy, right? But if I were to pick out a point there, okay, right away you should be able to tell me the sine of the x coordinate and the sine of the y coordinate. They're both going to be negative, right? Because look, I'm negative x and I'm negative y. Does that make sense? Okay, now let's take that idea. Let's take that idea because this is where one of the most common abbreviations comes from, right? I want to think about sine, cos, and tan in each of these quadrants. Sine, cos, and tan. Okay. Now remember. Yeah, we'll get there.
That's why it's
Okay, think about this with me. Remember, the cosine is the x value, right? So let's just do that for the whole diagram, okay? For cosine, right? Over this side of the diagram is cosine positive or negative? It's positive, isn't it? Because on this side, all the x's are positive, right? Whatever number you pick, the x will be positive. So cos will be positive here, and it will be positive here. Does that make sense? You cross over, all these values are negative, right? So cos is negative here, cos is negative. You can play the same game doing sine, except above the axis, sine is positive, 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 and below the axis, sine is negative. Okay, now tan we said was the ratio between sine and cos, right? So it's one divided by the other. So if I divide two positive numbers, what will the sign of the ratio be? Answer, positive. Okay, if I divide, it's sine on cos, isn't it? A positive number by a negative number, what will the sign be? Negative. If I divide two negative numbers, positive. And lastly, this is the same as over there, that'll be negative. Okay, now step back. Have a look at what we've determined. Over here in the first quadrant, it's the first quadrant because that's where you start counting, okay? In the first quadrant, all three of our main trig ratios, or should I say trig functions, they're all A for all positive. Okay.
Students take calculus.
As I go around the unit circle to different quadrants, I only ever have one ratio that remains positive, right? Over here, what's positive? S for sine. Down here, T for tan. And then over here, C for cos. So some of you have heard this as the acronym, starting from the first quadrant, A, S, T, C. Which, depending on who you ask, stands for all stations to central. Or
What is
if,
that, dude?
Or
Nobody says that, man.
add sugar to coffee, Or if you were, I don't know if anyone knows, at my old school,
All students.
down the road there was a comprehensive school which didn't quite have as good an academic reputation as James Roos. So there was a teacher who was very fond of saying all students to Cumberland because that's where you go if you don't understand.
Oh my god, that's Mr. Lee.
If you're no, in fact, Mr. Lee has another one, which is I don't know what this says about his classes, but he says all students take cocaine. So
I'm gonna use that one.
yeah, okay, well, obviously, you know, you were junior students, so he gave you the PG version, but you know.
Obviously, he thinks highly of us.
Yeah, obviously. So, okay, now, here's the thing though, okay? This acronym, I really dislike this acronym. I don't like it. The reason why is because, not obviously you guys, but many people learn it, ASTC, and it masks understanding what's really going on, right? All that's really going on is, look, my x and y's will be positive up here, because x is positive here and y is positive here. Look over here, x is negative, and y is positive. So that's why the corresponding trig functions will have the same signs. That's really what's going on. By all means, use all stations to central as a crutch, okay? To help you remember, to help you evaluate things, okay? But please, 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 know what's actually going on. It's just about x's and y's.
So, it can be negative, like sine can be negative and cosine.
Yeah. Sine, cosine of 120 degrees is negative a half. And if I come down to here, right, for instance, if I said sine of any angle between 180 degrees and 270 degrees, all the cosines and sines of all those angles will be negative. Okay?
Is that what your calculator would give you? Or
Yeah.
just,
Yeah. Go ahead. You chuck in, with the one we worked out just now, was cos of 120, and it'll tell you minus a half. Okay? Now, by the way, it's not that this thing is smart, it's just that this thing has been told to do this, right? So it gives you the right value. Okay?
Alright, I probably didn't need to watch all that, but
Okay, so there's sine.
I'll finish this, and then I'll watch the actual video that I was wanting to watch.
Well, let's think about it. What would tangent of theta be? Let me write it over here. Tangent of theta is equal to opposite over adjacent. So if we look at this broader triangle right over here, this is our angle theta in radians. This is the opposite side. The adjacent side down here, this just has length 1. Remember, this is a unit circle. So this just has length 1. So the tangent of theta is the opposite side. The opposite side is equal to the tangent of theta. And just like before, this is going to be a positive value if we're sitting here in the first quadrant, but I want things to work in both the first and the fourth quadrant for the sake of our proof, so I'm just going to put an absolute value here. So now that we've done that, I'm going to think about some triangles and their respective areas. So first, I'm going to draw a triangle that sits in this wedge, in this pie piece, this pie slice within this circle. So I can construct this triangle. And so let's think about the area of what I am shading in right over here. How can I express that area? Well, it's a triangle. We know that the area of a triangle is 1/2 base times height. We know the height is the absolute value of the sine of theta, and we know that the base is equal to 1. So the area here is going to be equal to 1/2 times our base, which is 1.
He explained this before. What section would it be? I don't think it was review. Intro to limits, properties, continuity. It was one video. I think it was before derivatives. Properties, maybe?
You get rid of this x minus that. Have you seen the other things we can do, and that'll wrap it up. So we're still have to have those symbols not. So I make this substitution, then this I'm gonna get if I multiply 1.
Yeah, okay. I remember this.
1 minus fractions.
Definitely want to see the proof of this, though.
The answer is, well, number 4, very good. So this is going to give you, I don't know, 8 to 3 inclusively. Look, now is a limit, and now it's, what's that going to give you? Because the reciprocal of 1 is 1. 1, because that is the unit circle. Unit there is no. My parents once told me that I had a stormtrooper mask, but I've never been able to find it, so I know they're lying. They're like, "Oh yeah, we bought that for you." It's like when you're like growing up and you ask your parents, "Have I ever been to Disneyland?" Like, yeah. But really, it was just a park down the street with some guy named Greg. So, same thing. That's Mickey Mouse. No, that's Uncle Greg. Okay. Okay. Let's try that. Let's try that. Oh, okay. Let's go through the process of finding a limit, all right? The first thing you try to do is what? Okay, you try to plug it in. So you plug it in, what's sine of 0? No, sine of 0 is not 1. Sine of 0 is 0. Over how much? 0. Can you factor sine? Have you ever been able to factor sine in your life? No. No. So can you factor out anything and cross anything out? Can I just cross out the x and x and get sin? Yay! No, that doesn't work, okay? Sine has to have something next to it. If you do that, you have sinned in mathematics. That's not acceptable. You can't do that, so we're basically stuck. There's no way to do this unless you want to just plug in endless numbers. There's no really a way to do this, but we're going to find a way to do it. You ready to find a way to do it? We're using some trigonometry. Here's our idea. Let's see if I remember how to do this in a while. First thing we're going to do, oh yeah, we're going to bound this. We're going to make up a triangle. So, what I'm going to do is take part of my kind of a unit circle, not really, and make it better. That's better. I'm going to take my unit circle. What I'm going to do is take an arbitrary angle. I can't be specific because, of course, we want this to work all the time. So I'm going to draw that. Now, what I'm going to do from this, I'm going to make up 2 triangles. I'm going to drop a perpendicular right from here. I'm also going to drop a perpendicular. It goes like that. Okay, so let me define a couple things. Firstly, we're going to call x our angle. Second thing, what do I need? I need this. I need that. Now what I'm going to tell you is if we need to solve for that, let's see. This is going to be our tan x. How far is this distance right here? From here to here. Why? So would you agree that, stick with me here folks, are you okay that x is our angle firstly? I'm calling this length y, okie dokie? and this is 1 from here to here. That's 1. Give me the relationship of tan x then. Sine over cosine, yes. In the specific instance with a large triangle. Tangent is opposite over adjacent, true? What's the opposite?
Y.
Y over
1.
1. 1, because that is the unit circle. Well, interestingly then, y equals tan x. So this equals tan x. Oh, let's see, one more thing. We also need this distance, and we need that distance right there. So let's say, what do we want to do? This coordinate is, what's the coordinate on a unit circle?
Square root of 2 over 2.
Well, that would be for a specific angle. What is it sine,
Sine
cosine, or
over-
cosine, sine?
Sine cosine.
Geez, I'm asking you, come on, you gotta know this. Agree? Okay. Because yes, sine x is typically y for an inside triangle. What that means is, I'll try not to screw this up too much for this inside stuff. That means that our x for this inside triangle is cosine x. Do you agree? That means that our y is actually sine x. Right? Now, also, what we're going to be doing is looking at this one gives our height, but also this one. That triangle right there. What we're going to be doing is comparing the areas of these triangles. So let me recap just in 30 seconds what we've done. We've gone ahead, we made up three triangles. This one just gave us the height. That gave us the height. This would be cosine, but more importantly, this height is sine x. Do you all agree with that one? Furthermore, if I call this y is equal to tan x because of the relationship of x and 1. You guys okay with that one? Okay. Now we're ready to compare the triangles. So we've actually got three things going on. I need you to see all three things. First, we have a big triangle. You see the big triangle, yes? We have a smaller triangle, that's this one. So we have big triangle, we have small triangle, and then we have sector. Do you agree with that? So what we want to do is consider the areas. We have big triangle, we have sector, and we have small triangle. Can you tell me how you find the area of a triangle? It's the area of a triangle. Or base times height over 2, yes? 1/2 base times. Let's look at the big triangle. What's the base?
1.
Base is 1. Very good. What's the height?
Tan x. or
Instead
y.
of y, let's say tan x. And to find the triangle, I divide by 2. I need to show a hand seeing if you're okay with the area of the large triangle. Base times height over 2, we have base 1. Height is y, yes, but y equals tan x. So I'm going to use tan x because I want everything in the same variable and all in x's. And then divided by 2. Let's do this small triangle, then we'll talk about the sector. Small triangle, that's this one right here. Not this too small one, but this one right there. Are you with me on that one? It's that one. And that's the big one. Okay. And then we'll talk about the sector in a moment. What's the base of my smaller
1.
triangle?
Height is sine x.
What's the height? The height of my smaller triangle? Sine x, not cosine x, right? Cosine x would be sine x would be the height of the smaller triangle because that is actually a point on the unit circle. Do you believe me? So that would be sine x. And then, well, oh shoot, sorry. I'm off 1. 1 times sine x over 2. Are you okay with big triangle and small triangle? You all right with that one? Do you know how to find the area of the sector? Area of a sector.
No, what are we talking about?
Which one of these are we talking about?
This is the sector.
Pie slice.
Area of the big triangle. Subtract the area of the small triangle. No.
The area of the sector minus the small triangle.
Sure. How do you find the area of a sector?
Use a big triangle.
So there's actually a formula for it. It's this. It is your radius times your angle over 2. Radius angle 2. You ready for the math magic? Ready? But you have to find one thing. You have to agree that the area of the sector is in between the areas of the big triangle and the small triangle. Would you agree with that? So it goes big triangle, then sector, then small triangle. True. So what we're saying here is that the area of the small triangle is less than the area of the sector which is less than the area of the big triangle. Agreed or not?
Yeah.
What can I do to the 2's? If I multiply all those inequalities by 2, which is legal, what happens to the 2's? 2's are gone. 2's are gone. So what I'm going to do is change this into sine x is less than x is less than tan x. Some basic algebra. Basic algebra. You okay with that so far? Now here's the cool part. What I'm going to do, I'm going to divide each of these 3 things by sine x. Where sine x is positive, it's in the positive quadrant. That's okay. We're talking about a positive angle right here. What that means is that we're not going to change around these inequalities. So then this does that. You still okay with that so far? We divided everything by sine x. How much is tan x over sine x?
1 over cosine.
Sine x squared.
Say it again.
1 over cosine.
1 over cosine, because tan x is sine over cosine, yes? Divided by sine, that means you flip, multiply. You're going to be getting rid of those signs. So you're going to get 1 over cosine. We're almost done. Here's what I'm going to do. I'm going to reciprocate each of those fractions. I'm going to reciprocate the 1, this x over sine x, and the 1 over cosine x. What that's going to do is also flip around my inequalities. If you reciprocate that, it's going to flip your inequalities. Does that make sense to you? That's a mathematical truth. So I'm going to have 1 still, because the reciprocal of 1 is 1, is greater than sine x over x, which is greater than cosine x over 1. Do you see this thing anywhere? Do you see it right in the middle? Do you see how it's squeezed between 2 functions? It's squeezed between 1 and cosine x. Does that make sense? Now here's the theorem. It's called the squeeze theorem. The squeeze theorem says if the limit of this goes to something and the limit of this goes to something, then the thing in the middle has to go to that same limit if these are equal. Does that make sense to you? It says I'm trying to take a limit as we go to 0. Agreed? So then the limit of 1. What's the limit of the number 1 as x approaches 0? Can you tell me that? What's the limit of 1? Doesn't matter what we're going to, right?
Yeah,
The limit's
it'd be
1.
Say all approach.
Tell
one.
me, what's the limit cosine x as x approaches 0?
Yeah, 1.
Now, what do you get with cosine of 0? What's cosine of 0? Cosine of 0 is?
1.
It's not 0.
1.
It is 1. Here's what that says. Check it out. This is by the squeeze theorem. It says that right now, if I take the limit sine x over x as x approaches 0, it was squeezed between two functions whose limit was 1 as we went to 0. It says the limit of 1 is 1. It says the limit of cosine as we approach 0 is also 1. What does this limit absolutely have to be? If it's between those two functions, the limit has to be between those two functions, only they're going to the same number. What's that limit? It has to be 1. It's squeezed. It's saying the right bound is 1, the left bound is 1. Can it be anything different than 1? No. It has to be 1. Technically, I'm supposed to have these throughout the whole thing. And that's the big punchline for this part right now.
We're not done with these, are we?
No.
Can't get it.
So again,
No.
what we just did, we learned one thing about this. We learned last time that the limit as x approaches 0 of sine x over x was equal to, what was it equal to, do you remember?
1.
Okay, and again, for last time, we did not prove the squeeze theorem. We used the squeeze theorem to prove this thing. We bound it between two functions whose limit was 1. Therefore, this was in the middle of it. That limit had to be 1 as we approach 0. So this equaled 1. That's number one thing you gotta remember. You gotta remember that one, that's gonna be in your head, right? So memorize that thing. When x approaches 0 of this function, you get 1. If x approaches anything else besides 0, well, it doesn't matter. You can just plug that number in. Okay, that's fine. Now, there's a couple of them that we might also want to know. Is there a relationship for cosine, firstly, and is there a relationship for tangent? We're going to look at those today. Then I'll show you how to put everything together and do any limit, well, that's reasonable, of some trigonometric functions. You ready for it?
Yes, yes.
It's no Monday excuses this time. It's not Monday. It's Monday. Monday. No, it's Tuesday. I got you Tuesday. And Wednesday. Friday. It's Friday. Okay, I can understand that, but no. It's Tuesday today. We're rolling. So, number one thing. Number one thing. Can we find the limit as x approaches 0 of this? One minus cosine x over x. Well, let me ask you the question. Can you just plug in the 0? If you do plug in the 0, what do you get? You get 0, 0. What's cosine of 0, folks? You didn't know that. Cosine of 0 is 1. So on the numerator, you get 1 minus 1. That would be 0, right? And of course, if you plug in 0, x would become 0. You get 0 over 0. That's a problem. Can you factor 1 minus cosine x and cross out the x on the bottom? There's nothing we can do with that. We're going to have to find some way around it, just like we did with this one. Are you ready for it? It's not going to be nearly as time-consuming or mentally consuming as this one was. Okay, this one's actually quite basic.
What was the other thing in that video? I know the one we need to memorize is this one.
Six that we're going to be working with.
Okay, it's this. He's about to prove it right now. Alright, nice.
Here's what I'm going to do. What I'm going to do is find some way to see some sort of an identity in here. So what we're going to try to do is work around this 1 minus cosine x. And one thing I can do, perhaps multiplying by the conjugate would help us. Remember what the conjugate is? Just changes, what about that? Yeah, that's it. So in our case, the conjugate would be 1 plus cosine x over 1 plus cosine x. Okay. Well, let's keep this going. Then I've got a limit as x approaches 0. The denominator is now x times 1 plus cosine x. You guys okay on the denominator? I haven't distributed anything, I'm just putting those together for right now. Now, could you tell me, on the numerator, let's do a little work here. What am I going to get if I multiply 1 minus cosine x times 1 plus cosine x? What would you get out of that? Okay, try it on your own. If you can't do it in your head, try it on your own. Distribute it. Foil it out. You know you've got this, right? You know you've done that. The first thing you should be getting is a 1, yes? Then you're going to get plus cosine x, and you're going to get minus cosine x. Do you see that? What's going to happen to those middle terms? They're gone, so we're going to have 1. And then lastly, you're going to do cosine x, cosine x. Is that going to be a plus or a minus? Minus what? Cosine, not just cosine x, cosine. Yes. Oh, now here's the deal. Using your massive knowledge of trig identities, some of you have and some of you don't have right now, to be the brutally honest truth, what is 1 minus cosine squared x equivalent to using the Pythagorean identity? Oh, you do have that knowledge. That's awesome. Very good if you know that. That's right. Because, listen, if sine squared plus cosine squared equals 1, if that's true, which it is true, and if I try to make this out of this thing, that would be subtracting cosine, right, from both sides. If I do that, we make up another identity. We make up the identity 1 minus cosine squared x is equivalent to sine squared x. Therefore, this thing is equivalent to sine squared x. Can you follow so far? Now, we're going to do a little bit of algebraic manipulation. I have gone from this, I multiplied by the conjugate. I've used the Pythagorean identity in a unique way to get sine squared x.
Let me try and do this part on my own. Is this cosine
Not much of this at
squared?
all. I just said x times 1 plus.
No, okay. This is the limit. Zero over 1 plus 1. 0. Okay, makes sense.
Plus cosine x. You follow so far? Now, because this is a limit, I can split up limits by multiplication, true? So I'll show you every step by step. Watch what we can do here. With our sine squared x, I know that I could make this limit of sine x times sine x. Is that not still sine squared x? Okay. Again, as x approaches 0. And then this thing, I'm not going to distribute that. I'm going to not distribute it for a very specific reason. Check this out. This is the same thing as x times 1 plus cosine x. So I haven't really changed that at all whatsoever. You still okay with this? You sure? Raise your hand if you are. Feel all right with that. Good. Okay. Basic algebra. Here's the idea. Look at, because we can separate limits by multiplication. Check out what we can do. I can group together, because it's just fractions, this thing and this thing. Do you see it? Does that thing look familiar? Yeah. So if we group it, then this is going to be the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of sine x over 1 plus cosine x. Very brief recap, very brief. We multiply by the conjugate. What that does is create a sine squared x for us. The sine squared x can be split up into sine x times sine x. The x times 1 plus cosine x, we don't change that at all. What we do is we group it in a certain way so that we can use a previously known identity that we have proven. That's okay. We're using something we've already proven. So now we have a limit of x, sine x over x, and a limit of sine x over 1 plus cosine x. It's okay to split up limits by multiplication. I taught you that property. Are you still okay with this proof so far? All right. Can you tell me how much is the limit as x approaches 0 of sine x over x? 1. Beautiful. We just did that, right? We just did that. That's fantastic. So this is 1 times. Now, what I want you to do is I want you to try to evaluate this limit at 0. Are you going to have a problem with that? Are you going to have a problem? Why not? Why don't you have a problem now? What's sine of 0? Good. Is it okay to have 0 on the numerator?
Yeah.
Sure. Does it make 0 on the denominator? No. Because you have 1 plus how much? 1 plus 1. That's 2. You have 0 over 2. This is 0 over 2. Agree? So how much is 0 over 2? 0. What's 1 times 0? 0. Don't say 1. How much is 1 times 0? 0. What that says to us is we've just proved something else. We now have this identity. That's identity. The first one we did, number 1. This is the second one. The limit as x approaches 0 of 1 minus cosine x over x is 0. Interesting. You know, maybe you can remember it this way. Well, I do at least. I remember it this way. Something involving sine gives you 1, something involving cosine gives you 0. That's kind of interesting, right? Because usually it's, if sine gives you 0, cosine gives you 1, right? If cosine gives you 1, sine gives you 0. It's almost the same idea here. The sine one is giving you 1. The cosine one is giving you 0. It's kind of cool, right? Same sort of relationship. That's how I remember it, at least. Would you like to do the tangent one? Tangent one's even a little bit quicker. Actually, much quicker. Let's try to find tan x over x. Now, could you just plug in the 0? What's tangent of 0? What's tangent of 0? 0 because sine is 0. And cosine would be 1. That would be 0. But now you have it over 0, so you have 0 over 0 again. So we do need to manipulate it. But here's what we can do. How much is tangent as the identities say it is? So sine over cosine. So we could make this that. Are you okay with that one so far? If we do a little bit of work with this, just a little bit, remember this is like x over 1. You're going to, instead of dividing, reciprocate and multiply, true? So this would be the same thing as the limit x approaches 0 of sine x over cosine x times 1 over x. Still true? Still true. Now, all I'm going to do, because of the commutativity of multiplication and what we can do with fractions, I'm going to interchange this with that. Is that okay with you? Just going to flip them. Why? Well, does it matter the order in which we multiply? And this is fractions, right? So I can make everything one fraction. True? So that means I could make it one fraction, commute the denominators, and then split it back up again. So that means I go, okay, that's the limit. X approaches 0 of sine x over x times 1 over cosine x. I've just switched those two things, and that's fine. You can do that because multiplication is commutative, and you can make one fraction out of that by multiplication. See anything interesting? Have you seen that we're trying to get this thing all the time? Because we know what that is. Do you see the sine x over x? We can still split up the limits. So this would be the limit x approaches 0 of sine x over x times the limit x approaches 0 of 1 over cosine x. Interesting, interesting. Hey, now that you have this memorized, I hope you do. What's the limit as x approaches 0? Don't read the board, right? It's right up there. Just kind of, hopefully you memorize it already. Limit as x approaches 0 of sine x over x, what is that? 1. So this one is 1 times, can you plug in the 0 now? Sure, what's cosine of 0? 1. It's 1. Yeah, what's 1 over 1? 1. Okay. What's 1 times 1? 1. You said 1 a lot today, haven't you? That means the limit x approaches 0 of tan x over x equals 1. Just like that. Just like that one did. Interesting. Like it so far? There's basically 3 things we need to know. These are the 3 limits we need to know of. We need to know the limit as x approaches 0 of sine x over x, that equals 1. We know the limit as x approaches 0 of 1 minus cosine x over x, that equals 0. And tan x over x equals 1 again. If you know those limits, you can break down all the ones I'm going to give you into those 3 identities. If you can do that, this is very easy to master. But it involves some thinking outside the box in certain cases. Would you like to see some examples of how to do that? Okay, let's start over here. Just memorize those 3 properties of limits, all right? Those are the proofs that we just did. Also, I'll say it's got to fit those pretty darn perfectly in order to be true.
Okay. Can watch the actual video now.
A lot in this class, okay? Yeah, memorize. Those derivatives. I'm not going to show you all of them. I'll show you one of them. The other, I'll show you sine right now. The one for cosine is very similar. The one for tangent, cosecant, secant, and cotangent can be done with the quotient rule. Because once you have sine, you have a lot of it pretty much done. You ready for it? We'll start today. We probably won't finish today, but at least I want to get started. What we want to do is if f of x equals sine, I want to find f prime. Well, here's what we know. We know that to take a derivative, here's why we need limits again. We're going to go back to the concept of a derivative as being a limit. Remember that we took a limit as h approached 0 of f of x plus h minus f of x all over h. And you thought you'd never have to deal with that again, right? We're going to deal with it a couple more times to figure out some derivatives that we don't already know, and this is one of them. We'll get to what this is and what this is, and then we'll stop. We'll come back to this on Monday. But remember how I had to do f of x plus h and f of x? in our case here, can you verify that f of x would be sine x, and f of x plus h would be sine of x plus h? Are you okay with that so far? One thing you need to know when we're going through this, you can't separate this x plus h unless we can use a trig identity. And we will use a trig identity, but you can't just pull that h out. Or you can't just do sine x plus sine h. That doesn't work. So we're going to have to use a trig identity. I'll show you that later. But for right now, here's how far we've made it. We know that the first derivative will be the limit as h approaches 0, sine x plus h minus sine x over h. Are you okay getting down to that part, folks? You see where that's all coming from? Cool. We'll continue the rest of this next time. So, well, we're right in the middle of this proof. We're trying to prove the derivative for f of x equals sine of x. And what we're doing is using the limit to prove that because, well, that is a derivative. The other stuff, we were just kind of shortcutting the derivative. So you need to know that this function right there, that is the derivative function. So we got to use that for most things. In case we know it's a polynomial, can finagle it with our product rules or quotient rules. That's really how we find most of the derivatives. So here we've made it down. We know that f of x is sine x. We know that f of x plus h is sine of x plus h in parentheses. We're going to use one trig identity with this, and then we're going to try to get these two identities out of it. And if we can do that, because those are limits, then we'll be able to find the derivative. So here's our idea. As soon as we make it down to sine of x plus h, we're going to use the addition rule for sine, which says you can split those things up like this. You can say this is equal to, you can look up that identity on your own if you'd like. Sine of x plus h, in those parentheses, is the same thing as sine x cosine h plus cosine x sine h. So this part right here is the same as this part right here. Those are the same. So I still have a minus sine x. All over h. Are you familiar with that identity? Have you ever seen that before?
Yeah, I just can't remember which one it's called.
It's the addition. It says you can separate the addition of that angle like this. Sine of x cosine h plus cosine x sine of h. Now, I'm just going to interchange these two things real quick so I can have my sine of x next to this sine of x. I'm going to end up probably factoring that out. Actually, I'm definitely going to be...
Wait, is that a plus?
Factoring that out. Cosine h plus
Yeah, I don't know why it's good.
cosine x
Oh, it's weird, he was dividing it.
sine h. So this part right here is the same as this part right here. Those are the same. So I still have a minus sine x. All over h. Are you familiar with that identity? Have you ever seen that before?
Yeah, I just can't remember which one it's called.
It's the addition. It says you can separate the addition of that angle like this. Sine of x cosine h plus cosine x sine of h. Now, I'm just going to interchange these two things real quick so I can have my sine of x next to this sine of x. I'm going to end up probably factoring that out. Actually, I'm definitely going to be factoring that out. So let's just go ahead and interchange this term with that term. So sine x cosine h minus sine x. And then plus this thing at the very end. Are you okay with that so far? Sure, so just reverse those things. Now notice that this whole thing is over h, right? Which means I can separate each of those top parts as over h if I really wanted to. True? Make 3 different fractions. What I'm going to choose to do is a unique thing. I'm going to make 2 fractions. I'm going to make this one over h plus this one over h. And you might see y already. Do you see y already?
Mm-hmm.
Do you see a sine h over h right now?
Oh, is he gonna factor?
Anywhere? On the right-hand side, there's a sine h over h. We're going to be able to use that. On the left-hand side, we see a sine x and a sine x. We're going to be able to factor that out. So we're going to factor the sine x out here. I'm going to make this look just a little bit different. I'm going to do cosine x times sine h over h. Last little thing, if you really want it to look identical, I'm going to factor out a -1. See how it's cosine h minus 1, and we have 1 minus cosine h. You see that? Actually, this is also another identity. I think they give it to you in the book, as a matter of fact. It's the same exact thing. If we factor out a -1 from that, you could do, just to make it look identical, this would become a negative sign times. If I factor the -1 out, those will reverse. I will get 1 minus cosine h. The cosine will become negative, the 1 will become positive. If you really want it to look identical, I'm going to factor out a -1. See how it's cosine h minus 1, and we have 1 minus cosine h. Do you see that? Actually, this is also another identity. I think they give it to you in the book, as a matter of fact. It's the same exact thing. If we factor out a -1 from that, you could do, just to make it look identical, this would become a negative sign times. If I factor the -1 out, those will reverse. I will get 1 minus cosine h. The cosine will become negative, the 1 will become positive.
That's a better way of writing it, isn't it?
Over h. Yes, no? Are you guys okay with our algebra so far? Yeah.
I got lost where you got the cosine h minus 1 from.
I have factored out sine x from this term and that term. So if I factor out sine x, I get cosine h. If I factor out sine x, I get 1. Factoring means division, so we're dividing.
Alright.
Yeah.
Where does the h, how come the cosine over h, and it's not cosine over h in the second one?
This one?
Yeah, where did it?
3x over 2 is the same thing as 3 times x over 2. Good questions. Any other ones? You all right with this so far? You okay that factoring out a negative will reverse those 2 terms? Good deal. See anything that pops up in our problem? Yeah, we see some identities, right? And because limits are separable, we can separate those.
Oh wait, this is 1, isn't it?
Those limits by addition. Further by multiplication. We can separate limits like that, not derivatives, but limits, and this is now a limit.
Ah, true.
What is the limit of 1 minus cosine h over h? How much
It's up here, 0.
is this? 0. So negative sign times 0, that's going to give you 0. That part gives you 0. Are you okay with that? Are you sure? You can do one more step if you want. This is, remember, okay, let me make one more thing clear. What is going to 0? The h or the x? The h is going to 0, not the x, the h. So the x's stay the same, just like you do with your derivatives. You remember doing your derivatives with limits? Your x's stay the same. So this would be negative sine x times 0. That's going to give you 0.
Oh, okay.
Plus, what happens to the cosine x? Does it go to 1? No, cosine x stays the same because it's an x, that's not an h. Cosine x times, what's sine limit of sine h over h? How much is that?
1.
0 plus cosine x. Cosine x. Is that interesting? No. No. Don't care. You're gonna care. It better be interesting. You're gonna have to memorize it firstly. It says the derivative of sine is cosine. What's the derivative stand for? Which is weird, right? Because it says find the slope at any point on sine. Plug in a number into cosine, you have the slope on sine. That's weird. It's kind of unique. We proved it though, right? Were you able to follow the proof? So now, do we have to do this again? No, you don't have to do it again. You now have the derivative of sine. The derivative of sine is cosine.
Is it reversible?
No, I'm going to give you all of them right now. It's not exactly reversible. The derivative of cosine is not sine. Okay, it's not sine. It's close to that, but it's not sine. I'll give you all those right now. I'm not going to show you the proofs. The proofs are for cosine are done very similarly. Okay, you do cosine very, very much the same as this. Very similar to this one. Let's see if I can. Then you'd still separate it. You'd still do your factorization, but you'd end up with having a negative up front, and that's going to be what we get. Well, you're going to see that in our derivative of cosine right now. So derivative of sine x is what, folks?
Cosine.
Good. So whenever you see that from now on, you got it. That's it. Let me give you the rest of them. This will be kind of like a memorization table for you. You've got to know this stuff. Are there any questions on this anymore before we continue? All right. So here we go. If you want to take a derivative of sine, you know it's going to be cosine. That's our number one. Now, the derivative of cosine, again, you can find it doing the same thing that we did. Turns out that it's not exactly sine, it's negative sine. Negative sine. If you want to see that, come and see me, I can prove that to you. But once you have those ones, check out what happens. What's tan x? What's tan, well, I'm
It wouldn't be negative sine x over cos x, would it?
sorry, not the derivative of it, but what is tan x, the identity? It's what?
Or negative cos x over sine x?
Over what? So with the quotient rule, you could find tan x, because you'd have sine over
Oh,
cosine,
quotient rule.
quotient
Okay.
rule, work it all out, simplify it, and
Right,
what
I
you're
can
going to
still
end
use
up with is secant squared x. So the derivative of tan x is secant squared x. Again, if you want to see these, well, I don't know if they prove them in your book, but you can come and see me, and I'll show you the or do the quotient rule on your own. That might be an example for you to try later. Do the quotient rule on sine over cosine. Do you see what I'm talking about, sine over cosine? Do the quotient rule on sine over cosine. It'll work out eventually to secant squared x. It might take a little bit of trigonometry to get there, but it will. There's three more. Let's try secant. What's the derivative of secant x? Well, notice how secant is really 1 over cosine, isn't it? You could really do a quotient rule with that if you wanted to. The derivative of 1 would be 0, though, so that might be kind of nice for you. Over the cosine squared, what's going to end up working out for you is secant tangent. Secant x, tangent x. If you did, what's the next one I want to do? Cosecant. Derivative of cosecant, well, cosecant is 1 over sine, so if you did the quotient rule again, you should be able to find out what cosecant is. This is negative cosecant cotangent. Last one. What'd I miss?
Cotangent.
Make sure I'm right. Yeah. Negative cosecant squared x. I really should have these switched so you really see something about it. I'm not going to, though, because that would involve me rewriting it, and I really don't want to do that. So look at a couple things. Firstly, sine goes to cosine goes to negative sine. If you look down here with these really should be opposite to match up with the cosecant and secant. You see what I'm saying? The cosecant would match up with our sine, but it gives you a different sign. So negative. The secant gives you the positive that's a different sign. But look at this. Secant, cosecant, tangent, cotangent. That kind of matches up a little bit. At least you can make that similarity there. Also, if tangent gives you secant squared, cotangent gives you negative cosecant squared. You see the secant-cosecant relationship, the square, positive, negative. So learn those ones. Maybe you can get a relationship in your head, how to remember it. I remember that in that certain way, so that's how I do it. But you're going to need to memorize those because they come up a lot. So you're going to find those out a lot and a lot and a lot. You got those? I don't expect you to memorize them right now. So if I go, cotangent, you're going, I don't know. Well, cosecant, cosecant, yay, got it. But ultimately, you need to remember them for the test and things like that. Okay, for your homework, you'd go a lot quicker if you didn't have to look them up all the time. Well, I'm going to leave those on the board. Would you like to do a couple examples on how to use these?
Sure.
Of course. Yeah.
One day we should all act like we're into it.
What do you mean act?
Like in drama class, you know? Act. This is the highlight of our life.
This is the highlight of your life.
He's gonna break his pen.
Like, this is literally, without calculus 1, you can't do calculus 2 or 3, differential. Your next classes are worthless. If you can't do this, it means you won't get a job. You won't get married. Unless you're already married. If you don't finish this, you'll be divorced. No, I'm just kidding. Just kidding. Kidding. You won't get a job, no money, no car, no girl. It's Friday. You got no job. You don't want to end up like that, right? So this is, what did you say it was? The highlight of your life. No, it's the highlight of your life. I think that's the straw man logical fallacy.
That's
Actually,
just slippery slope, actually.
I thought it was building up something. And
Slippery slope. I have Phil 10 right now.
what did I do? Slippery slope?
Yeah.
I just slippery sloped you all. Tell them Mr. Leonard slippery sloped me. Just make sure they know the context.
So weird.
I don't know. Kids are weird.
Please subscribe. At the end of every video.
Okay. We're trying to get into one of these forms up here. Um. Oh wait, would you just use the product rule? Because the derivative of sine x is cos x. Let's try that. What's the product rule again? Okay, so we got x times the derivative of sine x, which is cos x, plus derivative of x this would just be x, wouldn't it? Or wait. One? This be 1. Okay, 1, yeah. Sine x cos squared x plus sine x alright, we'll see if that's right. I feel like I was supposed to get sine squared x for some reason. Because then that would give 1, wouldn't it?
I want us to find the derivative for y equals x sine x. That's my goal. That's what we want to do. Now, I'll tell you what. I have a lot of people right now who are going to do this because they don't see something that they should be seeing. A lot of people, if they look at that the first time, they go, oh, well, that's very easy. The derivative will be cosine x. 1 times cosine x. You see how they could make that mistake? What do you need to do in order to do this derivative? Explain why it's a product rule. I have a function of x times a function of x. You see it? That's important for you guys to start seeing that stuff. So that's definitely a product rule. So we're going to have to set up the product rule. Go ahead and set it up. Derivative of the first times the second plus the first times the derivative of the second. Set that up. After that, it's almost a non-problem. These ones are kind of nice. Or this one is. Okay, that's the appropriate way to set that up. That's the product rule. It says the derivative of the first one times the second one, plus the first one times the derivative of the second one. Do you have that on your paper, or something that will match that? Okay, cool. Now, we take it where the ddx's are. We don't take derivatives of things that don't have an immediate ddx. That says take the derivative of this little piece. What's the derivative of this little piece? Okay, do it.
Wait, why did like swap them? I know it doesn't matter, but it's kind of strange.
Take the derivative of that. So that should still be 1 times sine x. You follow? So sine x. Plus, do I take the derivative of x? So I'm going to leave it x. Do I take the derivative of sine x? And what's the derivative of sine x?
Cosine x.
Good, not negative cosine x, just cosine x. Times cosine x, so cos x. So our derivative is sine x plus x cosine x. What's it stand for? What did we just do?
Slope.
That's the slope.
Oh wait, this wouldn't be cos squared x, because It's just x. If it was cos x times cos x, then it would be. But it's not. Okay.
So this is the slope of that. This is a slope function for that curve. So everywhere we want to find the slope, we just plug in that point to here. That would give us a slope of that. Are you with me on this so far? I want to do a specific one. I want to say find the tangent line. Give you an easy one. At x equals pi over 2.
Okay. Pi over 2 times cos pi over 2 plus sine pi over 2. So be pi over 2 times, that's the x value, so 0 plus, that's the y value, so 1. So the slope of the tangent line is 1. If you plug pi over 2 into the original, pi over 2 times sine pi over 2 sine pi over 2 is 1 times pi over 2, y equals pi over 2. The point is 1 pi over 2. I guess it would be pi over 2, pi over 2. Y minus pi over 2 equals 1 times x minus pi over 2. X minus pi over 2 equals y minus pi over 2 plus pi over 2 plus pi over 2. Y equals x. It's the equation of the tangent line.
Hey, tell me something. What two things do you need to make the equation of any line?
Slope.
Point, slope. Okay. Do we have a point yet?
No.
Not really. A point has something called something. We only have a something. So we don't have a point. Do we have a slope?
Yes.
Kind of. We have a function that will give you the slope. Do we have either right now the way it is? No. What I want is I want an m equals, and I want a point. That's what I want.
I'll use the top function.
Well, let's talk about that. If I wanted to find the slope right now, I have a function for the slope. Would I plug in to here to find the slope?
No.
To here to find the slope?
Yeah.
What am I going to plug in to find the slope? Yeah, because that's my x coordinate. That will tell me the slope of that curve at that point, at the x equals that value. So let's plug that in. I'm going to have sine of pi over 2 plus pi over 2 times cosine pi over 2. That's what this looks like. Sine of pi over 2 plus pi over 2 times cosine pi over 2. It's going to help you if you know the basic angles of this. The basic cosine of pi over 2, pi over 4, pi, at least those ones. What's sine of pi over 2? What's cosine of pi over 2?
2.
So this is 1 plus pi over 2, yeah, it doesn't change, times 0. How much is this whole thing?
1.
So my slope is 1. Oh, that's a nice slope. Very cool. Yeah, weird, the slope is 1 of that. Are you okay with this? We just basically plugged that value into this slope function and got out 1. That's our expression. Let's do the point. What goes here? Good, because it's my x-coordinate. It says x equals pi over 2? Pi over 2. How can I find my y? Yeah, you know what? It even says it to you, doesn't it? It says y equals. So it says, what's y equal? Well, it tells you right there. Y equals something in terms of x. Plug in the x. So it's going to be x sine x. X sine x. Let's try. Y equals x sine x. So y equals, in our case, pi over 2 times sine of pi over 2. Sure, so sine of pi over 2, you all gave me that as 1. Pi over 2 times 1 is 1. Oh, no, it's not. It's pi over 2. Pi over 2 times 1, you're like, yeah, no. Pi over 2, sorry, got ahead of myself. Now we have a point and slope. Now go ahead and use y minus y1 equals mx minus x1 to figure that out. What'd you get? Why? What's that mean? This way?
Vertical one.
This way?
No.
Vertical?
Diagonal.
Vertical would be like this.
Diagonal.
No, this is like, yeah, like this. Y equals x. Yeah, it's a diagonal line. Slope of 1. No problem. So we can now find tangent lines with trigonometric functions as well, as long as we know how to take those derivatives. Be aware that the product rule and the quotient rule will appear here. It's going to happen. Would you raise your hand if you feel okay with this so far? Good. I'm going to give you one to do on your own. Let's see how good you are. Let's start here. I'll leave this on the board for you for a second. I'd like you to find the derivative of that.
This would be cos x. Well, okay, this can be split up by addition. So this should be 0. Derivative of a constant would be 0 times the derivative of whatever. Doesn't matter, it should be 0, right? You can factor this out, couldn't you? Factor out a cos x. Cos x over 1 plus cos x.
No change in line right now, just find the derivative, okay?
Yeah, I'm gonna make sure the derivative's actually right before I make a tangent line.
Remember, this is certainly a quotient rule, so low d high minus high d low, square the bottom, way you go. You also need to use parentheses where appropriate. Don't leave those things hanging out if you're multiplying by something. Did you get the same thing as I did? Low d high minus high d low. At least you said it right? Mm-hmm. Okay. Now we follow the ddx. That's all this calculus stuff is about. Follow the ddx. Go slowly, precisely. Get the right derivatives as you're going. So we have the formula set up correctly. Just follow the ddx and show your work. Now, if you try to do too much stuff in your head, I swear it's really hard. You got to go slowly and write lots of work out. I know that takes a tremendous amount of paper, but trust me, it's worth it. You want to get the right answer slowly rather than the wrong answer quickly. That'd be the wrong way to go. So here we'll have, do I take the derivative of 1 plus cosine x there? No. I need parentheses still because I'm multiplying. Times the derivative of sine x. What's the derivative of sine x, folks? Good. Okay, got it. Minus, I don't take the derivative of sine x. But I do take the derivative of 1 plus cosine x. What's the derivative of 1 plus cosine x? What happens to the 1? The derivative of 1 would give you 0. Then you do the derivative of cosine. That's going to give you a negative sign. So we're going to be multiplying here by negative. Make sure it's in parentheses because you're multiplying by a negative there. You're not subtracting. Multiplying by a negative.
I should have done it slower. It would be 0 plus negative sin x. Nice, you know. I see something here. Let me make sure. Sin squared x plus cos squared x equals 1, okay. Nice. So it'd be cos x plus 1 over 1 plus cos x, or cos x plus 1 to make it look better. Cos x plus 1. Cancel out 1 over cos x plus 1.
Sin x. All over, don't forget about that bottom, 1 plus cosine x squared. How many people made it that far? Good. Hey, calculus is done. Right. As soon as you finish that, there's no more as soon as there's no more ddx's, your calculus is over with. Now it's just algebra and manipulation of those rational expressions. Well, not even rational. Those expressions right now. So what are trigonometric rational expressions? So if we distribute here, we're going to get cosine plus good. Then what?
Plus sin squared. Sin squared.
Sine x squared is not the same as sine squared x. This is not. That is not the same thing. If you're putting that, this is an angle right here. We're actually squaring the sine. This is the same. Sure.
That's what I was writing.
that is that, right? But if you omit those parentheses,
Now you got something.
this is wrong. Okay, this implies this. That would be incorrect. Okay, you can't do that. You can't change those angles unless you actually use one of the formulas to change angles. So we're going to put our sine squared x like that. Are you all right with that so far? Cool, cool. Tell me something awesome that happens. Yeah, trigonometry is awesome. It's happening right now. Calculus, also awesome. It's happening right now. But something even awesomer.
Identity.
Yeah, what identity? You need to see the identity. Mhm. What's this give you? 1. That's a 1. Cosine squared x plus sine squared, unless I'm wrong. That doesn't happen very often. Just kidding. It happens all the time. But yeah, that's 1. So this is, that was funny and nothing. It must be Monday. You're killing me today. Cosine x plus 1 over 1 plus cosine x squared. Give me something else.
Take off the squared line.
Can you cross those out? Do you see how they're one entire term right now, well, factor, I suppose. One entire factor here with here. So that and that is gone. What's on our numerator still? And that's our derivative. Would you raise your hand and feel okay with this one so far? Good deal, all right. What did we just find again? That is a derivative, but what is a derivative? So we found a slope. That's a slope function. If I asked you to find an equation of a line through a certain point, you'd use that for your slope. You'd plug in your value to that to get your point, and then you'd use y minus y1 equals x minus x1. Same ideas. Are you guys all right with this so far? By the way, if I asked you for... So a different example. That, could you do it? Okay, what does that mean, by the way? Just a second derivative. Let's take the second derivative, so let's find that. What's the first derivative, please? Okay,
Oh, it's a loop. Or no, it's not a loop, because it would be negative sine x. Wait, how did he write this?
Find the second derivative.
Or no, what's the other way?
Sure. Derivative of cosine is negative sine x. What's a third derivative? Say it again. Negative cosine x would be the third derivative. Are you with me on that? Negative cosine, because if we have negative sine x, the derivative of sine is cosine. This is negative cosine if I take the derivative.
Okay.
How about the fourth derivative? Why? Derivative of cosine is negative sine. Negative times a negative gives you a positive sign. That's interesting. It's really weird. How about the fifth derivative?
It's a loop.
6. Let's see. Fifth derivative, sixth derivative, 7, 8, and back and forth. Oh, it's cyclical. So when we take the derivatives of sine like that, it's kind of interesting. Unless we have a quotient rules, it is cyclical eventually. By the way, could you have done this if I asked you to evaluate this at x equals pi over 2? What's that mean to do? Just plug that in. You're going to get negative 1 in this case. You with me on that? So we can evaluate also, just don't forget what that means. This would mean that. This is 1, so we have negative 1. Still okay so far? Are you ready to try just a word problem that has this as some of its base? Yeah.
Is y cosine of x when you take it to the fourth derivative, is that due to the sine of x sine x period coming back to the same. Coming back, like it shows in the text that sine of x goes over and it shows where the derivative would occur for sine of x, and does that have anything to do with it oscillating back and forth?
Oh, it has a lot to do with oscillating, yeah. I mean, you got to figure that if the derivative of sine is cosine, that means that the slope of sine is cosine, but the slope of cosine is negative sine. If we keep on doing that, we're just finding, basically, the fourth derivative is a slope of the third derivative. If the third derivative is negative cosine, we're going to be getting sine out of that, which is, it's an interesting problem, but it does have to do with the relationship between sine and cosine.
So I think he's talking about the graph, like how it goes up and down like that.
Right.
Yeah.
Whether the fourth derivative has to do with that?
Where it oscillates, where because it goes, and it comes back to the same position once you go 4 times over.
We're not moving.
Oh, we're not?
No, we're not.
He's talking about the f of x graph for sine x, how it oscillates.
Oh, I get it. Yeah, I understand how it goes like this. Remember, we're talking about the slope of the entire function. So we're not saying as you go 4 periods to the right or 4 cycles to the right. That's not quite what we're doing. We're talking about the slope of the curve. So, for instance, it's going to be very hard for me to draw this, but this is the idea that we're talking about here. That's sine, right?
Mm-hmm.
That's the slope, right? Oh, mess up. Kind of pretty, huh? In a roller coaster. If you take and graph the value of the slope at every one of these points from here to here, and you say at x equals this point, the slope is this. X equals this point, the slope is this, and this, and this, and this. And you graph those, what you're going to end up with is actually cosine. Here's why. Slope of this point is actually 1. There. Slope of this point is 0. Ah. Slope of this point is negative 1. There. Slope of this point is back to 0. Cosine. Okay. Do it again. You're going to do the same thing, right? Slope is 0. Negative, 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 negative. That's where you're going to get negative sign. Right? You're going to go back and forth and back and forth. You're talking about slopes of things, slopes of, and the third derivative, the second derivative, the slope of the slope function. Fourth derivative, the slope of the slope of this. You're just talking about the slope of the previous function. Does that make sense to you? That's why you're getting these things. You're not moving at all. You're talking about the slopes of your function. That's the idea. Cosine. Okay. Do it again. You're going to do the same thing, right? Slope is 0. Negative, 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 negative. That's where you're going to get negative sign. Right? You're going to go back and forth and back and forth. You're talking about is actually cosine. Here's why. Slope of this point is actually 1. There. Slope of this point is 0. Ah. Slope of this point is negative 1. There. Slope of this point is back to 0. Cosine. Okay. Do it again. You're going to do the same thing, right? Slope is 0. Negative, 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 negative. That's where you're going to get negative sign. Right? You're going to go back and forth and back and forth. You're talking about slopes of things, slopes of, and the third derivative, the second derivative, the slope of the slope function. Fourth derivative, the slope of this. You're just talking about the slope of the previous function. Does that make sense to you? That's why you're getting these things. You're not moving at all. You're talking about the slopes of your function. That's the idea. Looks cool though, doesn't it? Pretty. Does that answer your question? All right. Now, for a real example, I'm not going to call this a super fun word problem because I got a comment on my little thing that was not super fun. So this is just a word problem. This is a super hard word problem. Hard. It's not. I'm just joking. No sense of humor today at all? Nothing? Honestly? Stand up next time. Maybe we'll get it.
I got that one. Was it one of your followers from Taiwan or?
I don't know. Okay, so let's say that you put a spring on the ceiling right here, and you attach a weight to it. It's going to stretch a little bit, right? Let's say you hold it real steady, and so it's stretching that spring and it's sticking there. And one of you jerks comes along and goes, boom, ha ha ha. What's it going to do? It's going to go, right, back and forth. Let's neglect friction of air and all that stuff. Is it going to do that forever? Let's neglect like friction and all that. Is it going to do that forever? Yeah, it's going to oscillate, right? It's not going to lose anything if we just let it go and go and go in a vacuum and stuff like that. Okay, it's just going to do that forever and ever. That's going to mimic a sine or a cosine function. As a matter of fact, if we look at this, I'll write out the example right now. We attach a spring and a mass stretches it 3 centimeters beyond its resting position. A spring is stretched 3 centimeters beyond its resting position. And released. So you go to the thing and go, and it goes, okay, so it's oscillating back and forth. At, let's make it at a certain time, at t equals 0. Let's talk about the position function. Let's talk about the position function. If you were to draw this, let's say this would be the spring, and here's the little weight that's attached, okay? And you're going to stretch this 3 centimeters beyond its resting position. So stretch implies that you're going to pull it down further, true? Are you going to start at 0 when you oscillate? Where are you going to start? 3 centimeters down. 1, 2. You're going to actually start at -3, true? And what's going to happen is it is going to go up, reach a climax, go down, and up and down and up and down. True? So it's going to go up, and then down, and then up, down, just like that forever and ever and ever. What does that look like? Does that look like a sine, a cosine, a positive sine, or a negative sine? Negative cosine. Sorry, a sine, a cosine, positive, negative sine, or a negative cosine? Which one?
Negative cosine.
Negative cosine. Negative sine would look like this, starting at 0 and going. This is a negative cosine, starting negatively and then going up. So if we were to,
it starts negative. Okay.
Make a model of this, we'd say it starts at -3, but it's definitely a cosine function because I'm not starting at 0. It's negative because it's like the reflection of a normal cosine. It's starting down here instead of up there. That would be +3. You okay with that so far? All I'd like us to do is talk about the velocity. The velocity of the mass at a certain point. So we know it's going to be oscillating back and forth, and really the velocity should be 0 here and here and here, shouldn't it? Because that's where it's changing, going up, going down. It's going to pop and go down. What I'd like to do is just find the velocity for this. Find the velocity function.
This would be 0. This would be negative sign. Negative sin x. Or t.
What's velocity as it is related to position?
Slope.
So basically just find the first derivative. So find the first derivative of -3 cosine t. First question I have for you, since I have -3 times cosine of t, do I need a product rule or not? Explain that.
Yes.
No.
Explain why I don't need a product rule
Oh.
here.
Oh, you can just pull out the -3. Crap.
Yeah, I don't have a variable at all. I don't have a function of t. I just have the number -3 being multiplied by that, right? And if I did the product rule,
You can pull it out in
you take
front
the
of you.
derivative of -3, that should give you 0. And so that would fall out of your equation anyway. You don't need the product rule for this. So this one we'd say, all right,
Forgot.
the -3 is a constant that will be there no matter what. So we're -3 times our derivative. What's the derivative of cosine of t? Can you tell me what that is? So -3 times negative sine t. I'm showing you a little extra step so that you can see what's actually going on here. -3 times negative sine of t. What's that going to give you?
3 sine t.
Now could I ask you things like, where will this curve have a velocity of 0? Could you find it now? If you set that equal to 0, you know what you're going to find? You're going to find this point, and that point, and that point. Every point where it changes from rising to falling or falling to rising. That would give you those horizontal slopes, right? That would be a velocity of 0, where it's changing. I could also ask you for any tangent line here. Let's say find the tangent line at pi over 2. Find the tangent line at 3 pi over 4, things like that. You should be able to do that as well. How many people feel okay with what we've talked about so far? Good deal. All right. Are you ready for the next thing? Yes.
Yes.
The answer is yes. Yeah, you are. I know, because I'm your teacher, I can tell. You're ready. Here's the next thing. The next thing asks this question. We're just going to do a little intro right now. It says, can you take the derivative of this? Can you take the derivative of that?
Yeah.
Of course you can. What's the derivative of that thing?
6x.
Cool. And if I did this, can you take the derivative of that thing? Really? How would you do it? Okay, you could use the product rule, couldn't you? You could do 3x squared minus 4 times 3x squared minus 4. You could do the product rule. Or maybe a little bit simpler, you could distribute this. True? And then take it term by term. Right? Well, that one. You can still do it.
Distribute it.
But you're going to have to distribute probably 3 times or distribute it once and then use the product rule. Either way, it's going to get a little bit more tedious, right? Okay. What about that one? You go,
You can use the power rule.
that's crap, not crad.
Oh, crap.
Crad, you Leonard. Yeah, no, not crad. Crap. Oh, crap. Why crap? Because this is ridiculous. You don't have to distribute that out 100 times. Or use a product rule like 5,000, I don't know, what is it, 100 times. You don't want to do that, do you? We're going to learn something that's called the chain rule. What the chain rule allows you to do is treat your function like a composition to get around the fact that you have a large exponent. Or treat your function as a composition so that you can get around something like this. Because I haven't showed you how to do that. The answer to this, write this down and cross it out, is never this. I'm going to show you how we can use compositions in something called the chain rule to deal with these two types of problems, because these two types of problems come up an awful lot. If you know the chain rule, you can deal with them very, very concisely. If you don't, you're stuck. You're stuck with this. Do you understand? Because I haven't showed you how to do that. The answer to this, write this down and cross it out, is never this. I'm going to show you how we can use compositions in something called the chain rule to deal with these two types of problems, because these two types of problems come up an awful lot. If you know the chain rule, you can deal with them very, very concisely. If you don't, you're stuck. You're stuck with this. Do you understand the idea about why we're going to learn the chain rule next? Then we're going to tie everything together. Chain rule is the last rule that we have. Then we're going to go ahead and combine product rule, quotient rule, chain rule, all that stuff. Make it real nice. You'll be able to do every derivative that I give you. I'm not a spontaneous person.
Okay, hand it there.